This is a review for PC 13, Graphing Exponential Equations. Graph each one, complete the table, plot the points. But to go back a little bit farther in math, first we're going to look at some linear equations, like y is equal to 2x. And we can plug in or substitute for x different values. 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, so on and so forth. And what is the pattern here? As x increases by 1, we are actually adding 2 each time. That's how linear equations work. Sometimes there's a b value like 10, and that tells you where to start at. When x is 0, you start at 10, but each time you just add 2. And that's how we can figure out those coordinates. For exponential equations, they work a little bit different. Our default value is to start at 1, because any number raised to the power of 0 by the 0 property of exponents is always going to be 1. So that's different from 0. And here our growth factor is 2, but instead of adding 2 each time, we're going to multiply by 2. And each time this doubles. And what you notice is that it grows a lot faster than adding 2. We got to 10, whereas here we got to 32. And very quickly, that's going to change even more. Similar to linear equations, where we might have a starting value of 10, if we did y equals mx plus b, there are starting values for exponentials as well. 5 here represents our starting value. And our growth factor is still 2, so we are doubling this. 5 times 2 is 10, times 2 is 20, 40, 80, 160. We can see that exponential growth can be very, very quick. On the opposite end of the spectrum, there is something called exponential decay. When our growth factor is less than 1, each time we multiply, we're multiplying by a fraction, which is really the same as division. Multiplying by 1/2 is the same thing as dividing by 2. So our starting value here is 4, from right here. And each time we go to the right, I'm going to multiply by 1/2, or divide by 2. So this becomes 2, 1, 1/2, 1/4, and 1/8. What you should notice is that exponential growth grows very quickly, and it will approach infinity, but of course never reach it. And exponential decay here approaches 0, but never actually reaches it. It might be 1 over 10 bajillion, but there's still going to be 1 on top of that fraction. It's never going to be 0. So on your calculator, I'm going to show you what this looks like graphically and how to build the table to solve all of these. So if our exponential is 4 raised to the power of x, zoom in a little bit, we want to fill in this table, plot the points, and sketch the graph. To start, we're going to go to y equals in the very top left. I'm going to press 4 and then the caret key right here above division. That's to the power of. And then I'm going to press the x key just to the right of alpha, 4 to the power of x. So I'm going to press second graph to pull up the table, and I'm going to copy these values into my table. 0.0625, 0.25, 1, 4, and 16. Notice the calculator gives you these values, but you could use the same technique that we used above. We start at 1 times 4 times 4. And as we go to the left, notice we divide by 4. This is the same thing as 1/4 and 1/16. Some people prefer the calculator method. Either way is fine. If we press graph, it'll show us a general picture of what our graph should look like. Plot a couple points, make them clear. 0, 1, 1, 4, 2, 16. And we can sketch what the rest will look like. Notice here on the left, it's a tail that gets really close to 0 but never actually reaches it. Moving on. 1/2 raised to the power of x. Anytime there are fractions, we're going to use parentheses on the calculator. So I'm going to press y equals again. I'm going to press clear to get rid of my previous function. And 1 divided by 2 in parentheses raised to the power of x. If I go to the table, I can fill in these values. Additionally, I can start with 0, and it's going to be 1. Double it as I go to the left, and halve it as I go to the right. Both of those techniques work. So I'll plot a couple of the major points here and sketch my graph. Notice on the right, it's going to approach 0 but never actually reach it. On to the back. Now my exponentials have starting values as well as growth factors. So I'm going to go back to y equals in the calculator. I'm going to type in 2 parenthesis 3 caret x. I'm going to press second graph to pull up the table and put these in. 0.2 repeating, 0.6 repeating, 2, 6, and 18. Now you might be wondering, how can I graph 0.222222222? Well, I would start with the easy ones to graph, such as 0, 2, 1, 6, or 2, 18. And I can sketch that part of the graph pretty quickly. And I know that on the left, it's just going to approach 0. So that's a pretty rough estimate. In combination with the table, definitely going to get credit. The next one, I go back to y equals. I'm going to type in 2 parenthesis 4 divided by 7 raised to the power of x. Second graph to pull up the table. Let's plug in some of those numbers. 6.125, 3.52, 1.1429, and 0.65306. So I'm going to start with the easy ones to graph, like 0, 2. And for negative 1, I'm going to go halfway between 3 and 4. It's about 3.5. And for negative 2 here, here's 6, so I just go a little bit above it. And as I go to the right, that's about the pace I'm going to follow. So I will sketch my graph. Notice I have my table. I have several points identified. And on the right, it's going to approach 0 but never actually reach it. Last couple problems. 5 to the 3 halves raised to the power of x. Go to the table. There's my values. 2.2 repeating, 3.3 repeating, 5, 7.5, and 11.25. This is where we'll find out pretty quick if people are just sketching their best guess at the graphs. Because if you plot this one correctly, you'll notice as you go to the right, it doesn't increase quite as fast because our growth factor is not as big. It's only 3 halves, or 1.5. And as we go to the left, 3.33 and 2.22. It's going to take a little bit longer to get to 0. And if you look at the graph, that is shown here. And if I change my window to get rid of the negatives, you'll get an even better look. It's going to look something like this. So if you're just trying to draw some swoops and get lucky, this one will separate the truth. It's still eventually going to approach 0. Last problem. A decimal works the same way. We'll go to y equals. We'll plug in 12 times 0.8 raised to the power of x. We'll go to the table, and we can write down some of these values. 18.75, 15, 12, 9.6, 7.68. So negative 2 is going to be around here. Negative 1, 15. 0 at 12. 1 is going to be at 9.6. 2 is going to be at 7.68. And eventually this will get down and reach 0. approach 0, but not actually reach it.